Alright, so, of course, just when I start a video, they start mowing the lawn. Whatever. So, section 3.1 is a little introduction to second orders. And I've mentioned this in a previous video that if there was a second order differential equation, there's going to be two solutions. And what I mean by that is this. So, we looked at this before. We looked at one like this before. This is a second order linear differential equation. And we remember we mentioned this, these are of the format e to the RT. And so what we do is we take, well, we need y prime, of course, is r e to the RT, and we need y double prime, r squared e to the RT. And so what we're going to get, of course, is something to the effect of, hey, if I put this in, I'm going to get r squared e to the RT plus 3r e to the RT plus 2 e to the RT equals 0. Once again, the e to the RT cannot equal 0. So really all we're interested in is this. Of course, that factors r plus 2, r plus 1, which means that our r's are -1 and -2, meaning that our solution is of the format y equals c1 e to the RT, well, e to the RT, e to the -t, plus c2 e to the -2t. Okay, and no real reason or rhyme why I chose with the -1t first and the -2t second. No rhyme or reason to that. Don't look into it in any way. Now, if I told you, hey, listen, we have an initial condition of 5, that's nice, but notice I have two constants. Well, I'm going to need two initial conditions, not x naught, you jackass. Why not? And we're going to also need y prime naught. Again, it's very similar to knowing this is my initial velocity, that's my initial displacement. Okay, that's the idea. So then if you look at this, you can have, well, y, let's put in zeros. Well, what happens when you put in zeros? You put in 0, you get 5. You get c1 plus c2 is equal to 5. If you take the derivative, you're going to get y prime nice. If you put 0 into that, you're going to get 7. Nice. And so it's a matter of solving this systems of equations. If you add, you get 12. If you add, the c1s go away. If you add, you get -c2. c2, of course, means it's -12, which means c1 then must be 17, I take it. Sounds about right. So that means my equation is going to be y equals 17 e to the -t plus -12 e to the -2t. Now, I always like to look at Desmos. It just makes me happy. We know what's supposed to happen here. So our equation was 17 e to the -t oh, fart. Nice, there it is. Oh, that's hot. Now, if you look at this, what's exciting about this is this. At x equals 0, or y at x, t equals 0, or x equals 0 in this case, we have 5. Was that what we had? That's what our initial condition was? Sure enough. Nice. What was our slope? Well, it was 7. Does that look right? I don't know. But you know what I could do, of course? I could just draw in the tangent line, which would be 7x plus 5. Oh, dude, it's a tangent line. It's perfect. What does that mean? It means my first derivative is 7. So, yay, that's my equation. I'm excited about it. Awesome. Okay. Cool. In these second orders, we will look at several others, of course. We could have the format, we could have repeated roots as well. So you could have y double prime plus 6y prime plus 9y equals a goose egg. Again, we can just jump right to it. It's going to be r squared e to the rt plus 6 r e to the rt plus 9 e to the rt equals 0. And of course, really, I'm just going to jump from here, straight to here. Okay. And you may remember, or you may not, from a video earlier, I said this would come back to us. When you have a repeated root, they will always be these guys. And so sometimes the book writes it this way. Oh, well. Sometimes the book writes it that way. Sometimes the book writes it this way. Oh, I should have used C's. That's what they'll use. Sometimes they write it like this. Okay? And so in this case, it is simply going to be C1 plus C2 t e to the negative 3t. Now, the reason they do that is because we need independent solutions. If they were both e to the negative 3t, they wouldn't be independent solutions. So when we talk about a second order having two solutions, they are independent solutions. This is not in any way a linear combination of that. In other words, they are independent. When you add them together, there's no way that they can just cancel one another out. Stupid neighbor who mows their lawn in the middle of the day. Anyways. So yeah, so just be aware of that. So that is how this comes about. Now, talk some more about it later on. There it is. So if you told me that y of 0 was 10, y prime of 0 was negative 2, well, 0, you stupid, was negative 2. Let's plug it in. Well, 0, this piece cancels out. This piece goes to 1, and you get C1 is 10. Cool. Let's take a derivative, shall we? So y prime, so the 10 cancels out. Well, that's right. So at this part, you mean you can do it two ways. You can distribute it out, or you can just do it like this. I'm going to take the derivative of this, which is going to be C2, and then times the second equation, plus the first, times the derivative excuse me, and then plug in 0. This piece here will cancel out. You're going to get minus 30 coming out of that guy. This piece here will just be C2, and then equals negative 2. So it looks like C2 is 28. So you'd have 10 plus 28t e to the minus 3t. See what that looks like. 10 plus 28x exp of negative 3x. Oh, that's nice. If you zoom in on that, maybe. Well, what do you know, friends? What? At 0, it's equal to 10. That's cool. And I feel like my slope was supposed to be negative 2. Oh, that's nice. And so that's just a quick way to check yourself, because remember, the initial conditions must be true that you found. Cool. So that's what you'll be looking at. Pretty straightforward. In section 3.1, note that they, I think, wave their hands at it. No, they don't even talk about it in section 3.1. It's later on, so we'll talk about it in a few chapters. But in notice that if this is a and you did this, negative 1 plus or minus the square root of 1 minus 36 all over 2. This is going to give you complex roots. And so that'll be coming up later on. Okay. Just remember that e to the a plus bi. Well, just remember that e to the at, e to the I theta is Euler's principle, or Euler's formula, which gives you a cosine of theta plus I sine of theta. So there will be more to come with that. It's a very important concept. But in section 3.1, we don't really go there. Now, So we do the first part that I talked about, and then the second part is something that I also mentioned just briefly, and that is the idea that, hey, are these equations, are they independent or not? Okay. So I'm going to kill two birds with one shotgun shell here on this deal and see what happens. So on this problem here, it's y double prime minus 3y prime equals 0. Okay, now I'm told that these are the answers to this equation. Okay, that's what I'm told. Who am I to argue? Whatever. Now, how would I find that out? Well, I could do it this way. If these is r squared minus 3r equals 0, take an r out. What are your solutions? They are 3 and 0. What is e to the 0? It's 1. What is e to the 3x? It's e to the 3x. That's cool. I'm not going to do that on this problem, though. Okay? I'm not going to do that on this problem. Instead, what I'm going to do, okay, is I'm going to see if these guys are independent of one another. And the way we do that is we use what's called the Wronskian, I don't have the hardest time spelling it, determinant. Okay? And the game is thus. You put your equations on the top. The next row down is their derivative. So what's the first derivative of this guy? It's 0. What's the first derivative of this guy? It's 3e to the 3x. And then I'm going to take the derivative and the determinant rather. And the determinant better not equal 0. If it does not equal 0, they are independent. If it equals 0, they are dependent. Okay? So cross multiply, that's that, minus 0 is, well, it's not 0. That's what it is. So yes, they are independent. So then my solution is simply going to be, y is going to be equal to 1 times c1 plus c2 e to the 3x. And then it's simply a matter of plugging in your values. So at 0, we get a 4. Well, yeah, at 0, this goes away, so you get c1 plus c2. And then take the derivative is equal to negative 2. Well, the derivative is going to be y prime is equal to, the derivative of c1 just goes away. And then you're going to get 3c2 e to the 3x. And at 0, it's equal to negative 2. So there you go. So your solution, okay, so that's your c2. Plug it in up here, you're going to get, 4 2/3, I guess. So C1 is 4 2/3, which is 14/3. So you're going to get 14/3 plus, or minus rather, 2/3 e to the 3x. And you are done, my friend. Okay. Here's another example. They want to know, are these solutions independent, yes or no? So I'm doing 2 of these kind of problems. So the last one I gave you a setup so you knew it was a second order or not. This one you don't know if it's second order, but you kind of do. This is one of my proposed solutions. It's as if someone just kind of hinted at me, hey, this might be a solution, Jay. And they want to know if these guys are independent. Well, that means we've got a second order differential equation. How do I know? Because there are 2 solutions. If it was a third order, well, then I'd have to have a 3x3 matrix, and I'll give you an example of one of those in a moment. So this guy here, oh, you dumbass, that's supposed to say sign. Okay, derivative of this guy is going to be minus 2 sine x plus 3 cosine x. And then this fella is going to be negative 3 sine x plus, or minus rather, 2 cosine x. So if you take the determinant, it's going to be this guy times this guy. minus minus 2 sine plus 3 cosine. All right, let's do it. This times this, negative 6 cosine sine. This times this is going to be minus 4 cosine squared. Minus 9 sine squared. Minus 6 cosine sine. And then minus, that's going to be minus whatever I got in here. So I'm going to add negative 6 cosine sine. And then I'm going to have plus 9 cosine squared. And then my plus 4 sine squared. And then minus 6 cosine sines. Okay. So that's going to become a plus. And that's going to be a minus. And a plus. And a minus. Let's see what we got here. Interesting. Interesting. Hey, guess what? They don't cancel out. So because they don't cancel out, this does not equal 0. What are they? They are independent solutions. Okay? It's that easy, friends. Not hard. Not a very hard concept at all, actually. Okay? Well, let's just try another one of those. Let's see, you had x, e to the 3x, and you had e to the 3x, and you had, I don't know, e to the x, e to the 3x times x squared. I don't know. I just made that up. Who knows? Are they linearly independent? Well, the answer is yes, obviously, because you can't multiply this by a constant and this by a constant and get this guy, for instance. It's not possible. A constant. Okay, so, but if you didn't know that, you need to use the determinant. So I'm going to use this as my top row. I'll do the easy one first. Okay. The determinant, or the derivative of this guy is going to be e to the 3x plus 3x e to the 3x. And then the derivative of that will be this. Brother, this one's going to be 2x. And then Judas Priest, what a mess. Okay. It's quite clear that if you do the determinant, it's going to be this guy times the determinant of this guy. Okay. And then, of course, it's going to be this guy times this one, and then this guy times these guys. Okay. It's got to be an easier way, you say. There is. Let me show you how. This is how I would actually do it if I ran into one that I had to do like this and I didn't really want to do it too bad. Oh, wait. I'm going to lie to you. I'm going to do this. I'm going to do x times e to the 3x. Now what I'm going to do is I'm going to stow that. I'm going to stow it as some variable that I never use. I'm going to go with L. Okay. And then I'm going to do, I'm just going to get rid of the, well, actually I'm going to put a squared in there. And I'm going to, oh, fart! Rats! Rats! Okay, let's try this again. You see what I did? I copied over the L. There we go. There we go. So this is M. This is L. And let's go change this one to N. There we go. Cool. So this is what I'm going to do. I'm going to set up a matrix. I'm going to do, I'm going to matrix. I'm going to do M, comma, N, comma, L. Doesn't really matter. That's just how I chose to do it. Semicolon. And then I'm going to take the derivative of M with respect to X, comma, the derivative of N with respect to X, and the derivative of, oh, fart, what did you do wrong, stupid? L, semicolon. It's a lot of work, but it's a lot less work than doing it the other way. Second derivative. And there's our big matrix, right? So what I need to do is I need to take the determinant of this guy. And remember, all I'm looking for is it equals 0. That's not 0, friends. So the answer is, are they independent? These guys are independent. Okay? That's how the Wronski determinant works. It's not very difficult. And by all means, if you're smart about it, you'd use a calculator to do the derivatives, okay? And then, well, the derivatives aren't hard. It's just like you take this times this and then simplify it, and minus this times this and then simplify it, and then times it times that when you're finished. No, it's gross, okay? So section 3.1, again, is the big takeaway from that is we need linearly independent solutions. That's what the determinant's about. And then also is the idea that whenever we have something like this, we know that we can have our y's are of the format e to the rt. And if it's a second order, there will be 2 of them. And if it's a third order, there'll be 3 of them, and so forth. Okay? That's the big takeaway from section 3.1.